This program looks at several applications of a single mathematical idea, the idea of a vector space. We'll see how the grid reference on an ordnance survey map gives us a two-dimensional vector space. We'll see how the representation of a building in computer software used by architects extends this idea to 3 dimensions. We'll see how the spin of a satellite can also be represented by a vector in a 3-dimensional vector space. And finally, we'll see how a musical note might be represented by a vector in a 50-dimensional vector space. One way to imagine a vector is as an arrow, starting at a given point. A different vector might have a different size, or it might have a different direction. And if you have 2 vectors, you can always add them together to get a new vector. The original vectors mark out 2 sides of a parallelogram, and adding them gives a vector along the diagonal. So to understand vector spaces, it's a good idea to begin with a straightforward example, the one about grid references on ordnance survey maps. But maps themselves have a fascinating history, and we'll take a look at that before getting into the mathematics of them. I went with Eleanor Smith to the Ordnance Survey headquarters in Southampton. So, Eleanor, this is Carl Calvert, who is the geodetic advisor to Ordnance Survey. So, Carl, when and why did Ordnance Survey start producing maps?
There were 2 reasons. One was just as a mapping exercise, really for defence purposes, the first being Culloden and the second one being the threat from Napoleon. And then at around the same time there was a discussion as to which was going to be the prime meridian, Greenwich or Paris. And one was a scientific reason and the other one was a defence reason.
These days, producing accurate maps is a relatively straightforward matter. With modern technology, measurements can be made very precisely, and the calculations needed to create the maps can be carried out automatically by computer. But 200 years ago, the most accurate measurements were the ones made with theodolites, like these.
I think the main thing that one must realise is that with the technology in those days, they could measure angles very much easier than measuring distances. And the one distance that they did measure was on Hounslow Heath, which is now Heathrow Airport. But that distance was measured with deal rods. It took a very long time to measure, and having measured it once, they didn't really want to measure lots of other distances. They then made angular measurements all around the British Isles, and by connecting this one distance with angles throughout the British Isles, they were able then to establish coordinates for the triangulation stations or trig points that they had produced.
So to construct a grid, were all these individual maps combined?
Almost, but not quite. Rather than an additive process, it's a division process. We work from the whole to the part. So having got these coordinates of these points around the British Isles, we can then construct our map, but of course you can only see so far. There were rivers, the technology was such that they could only make maps of counties or groups of counties, whereas later on they could in fact produce a map of the whole of the British Isles at one go.
We can see the problem with the older maps by looking at a part of Kent and Sussex. As we take maps at a larger and larger scale, eventually we can see the individual fields. This is the modern map at a scale of 1 to 2,500. The county boundary runs across the middle. If we compare this with a map from 1870, the obvious difference is that the map covers only part of the area, the part in Kent. The rest of the map is blank. The other county, Sussex, is on a different map. If you want to cross the county boundary, you'll have to put these 2 maps together, like a jigsaw. The trouble is, they don't quite match. You can't see the discrepancy on the screen, but in fact, there will always be a tiny gap or a tiny overlap somewhere. This has happened because the Earth is curved, and the maps have been drawn using slightly different projections.
In fact, any map on a flat sheet of paper has to represent the Earth's surface using what's called a map projection. One way of getting a projection involves surrounding the Earth with a cylinder. This cylinder touches the surface on the Greenwich meridian. This is a version of the map projection developed by Mercator, and it's called the transverse Mercator projection. And once we have a map on a flat surface, we can describe any point by using coordinates. But the parallels of latitude and the meridians of longitude are curved, and the meridians get closer together as we get closer to the poles. So a better coordinate system uses a rectangular grid.
When was the first grid introduced?
Just after the First World War.
Is that the same as the current national grid?
No, the first grid was in fact a military grid, and the second was a civilian grid that was in fact established by a parliamentary committee, the Davison Committee, in 1945. And this wasn't realised until after triangulation that wasn't completed until 1960. But this grid, in fact, is based on a transverse Mercator projection, as in fact the earlier one was. And again, all that it is just a projection of a 3D surface onto a 2D plane. And the grid is a system of Cartesian coordinates.
We'll take a map of Southampton to see how vectors arise when we use the national grid. The grid gives a map reference to each point on the map. It's a 6-digit number which identifies the point uniquely within a 100-kilometre square. The first 3 digits of the number give the distance east from the left-hand edge of the square, 38.8 kilometres. And the last 3 digits give the distance north from the bottom edge of the square, 14.7 kilometres. Starting here, at Ordnance Survey itself, we'll go to this school. That's in a north-easterly direction. The second part of each map reference tells us how far north we have to go. From 14.7 to 16.5 is an extra 1.8 kilometres. And the first part tells us how far east. From 38.8 to 39.7 is another 0.9 kilometres. That shows us going first north and then east. But it doesn't matter which we do first, so we can think of both movements as beginning at the starting point. And then the resulting movement takes us along the diagonal of this rectangle. We're thinking of the two movements as vectors, and the resulting movement is the sum of the two vectors. And that's a method we can use in general for combining two movements. When carrying out the movements, we follow one by the other. But we can instead think of both movements as vectors, starting from the same point. And then the combined movement is the sum of the two vectors, the diagonal of the parallelogram. Now a map is a two-dimensional representation, but we live in a three-dimensional world. The objects we see have height as well as length and breadth, and we look at them from different points of view. So how are vector spaces involved? When the Albert Hall was refurbished, the work was planned over an 8-year period. The building wasn't closed all that time. Instead, the project plan incorporated dates of future concerts, and a computer model could show the state of the concert hall at all the different stages of the project. Each image shown on the screen is a two-dimensional representation of part of the building. In fact, the plans and elevations used by architects are just like maps, and they're used to present the construction data in an easy-to-understand format. But unlike paper plans, these computer images aren't separate documents. Instead, they're generated as required from a master three-dimensional model. And that's where the vectors come in. There are many different objects inside the hall. Structural items like pillars, walls and floors. Furnishings like seats and lights. And each object needs to have a position. We need to know where it is inside the hall. But often the architect starts with a relative position, for instance, the gap between the bottoms of two struts. We can think of that as a vector. It has a length and a direction. Then if we know the position of the first strut, we can work out the position of the second. It's vector addition again, giving the diagonal of the parallelogram. Once calculations like these have been done for every object in the building, the three-dimensional model can be used to generate all the diagrams needed to complete the refurbishment project. The use of three-dimensional computer models is now very popular with architects working on large projects. The models don't just deal with the nuts and bolts of the project, they can also be used to impress clients. One of the most advanced uses of three-dimensional modeling is in virtual reality software. Here you continuously change your viewpoint within the model. With a widescreen display, it really feels as though you're inside the building, even if, like this airport terminal, it doesn't yet exist. There's a rather different way of using vectors in 3 dimensions that's important in the space industry. Although the position of a satellite can be represented by a vector in the same way as a position on a map or in a building, we'll concentrate instead on a different aspect, the rotation of satellites, and how that can be represented by vectors. To find out more about that, we went to Matra Marconi Space in Stevenage, where they build satellites. So, Eleanor, this is Jahangir Potra, who is a systems engineer. Jahangir, what sort of satellites do you make?
Matra Marconi Space makes a very wide range of satellites, from small ones to very large ones, like the polar platform that we make for the European Space Agency. We also make a wide range of satellites for different uses. We make scientific satellites, Earth resources satellites, communication satellites, and military satellites.
So where do you launch the satellites from, and what sort of orbits do they finally attain?
Well, because we make a very wide range of satellites, we use a number of launch sites which are suitable for different orbits. We use Cape Canaveral in Florida for certain low Earth orbit missions and also for geostationary missions. In particular, for geostationary missions, the launch site in Kourou in French Guiana is a very useful launch site because it's very close to the equator. In the future, we plan to use Baikonur in Russia for some of our missions. The orbits that we use range from very low Earth orbits to very high orbits, and sometimes we also use highly elliptic orbits. For geostationary ComSats, we use an equatorial orbit with a period of 24 hours.
How do you ensure that the satellites are stable in orbit?
Well, in transfer orbit, for example, before the satellite has attained its operational orbit, we often use the technique of spinning the satellite. This ensures inherently static stability. And this is important because when the satellite is in transfer orbit, it is not always visible from ground stations. And inherent stability is a very valuable asset.
The spin of a satellite is called its angular velocity, and we can represent it by a vector. The vector points along the axis of rotation, and the size of the vector represents the speed of rotation. Slowing the object down makes the vector smaller, but keeps it in the same direction. And when the spinning stops, the vector is 0. Spinning in the opposite direction gives a vector in the opposite direction.
How can you make a satellite spin?
Well, you can do it several ways. In some instances, we use little rocket motors called thrusters to spin up the satellite and also to despin it when we need to despin it. In certain other circumstances, the satellite actually carries a rotating wheel, which is called either a momentum wheel or a reaction wheel. And when we spin the wheel, the reaction from the wheel makes the satellite spin in the opposite direction.
Would you ever need to change the direction of the spin?
Oh yes, very often the spin state of a satellite is dictated by the phase of the mission that the satellite's in. In transfer orbit, for example, the satellite spins about its z-axis, and it spins at a reasonably high rate. Once the satellite gets onto geostationary orbit, it has to be Earth-pointing, and the spin state there is with the satellite spinning at a very slow rate once a day about the y-axis. So you can see that the spin state of the satellite has changed from a high rate about the z-axis to a very much lower rate about the y-axis.
We can use vectors to describe the way the spin changes. When the satellite first reaches geostationary orbit, it still has a spin it was given for stability. We represent this by a vector along the axis of the spin. It's horizontal in our picture. This spin needs to be changed so that the satellite locks onto the Earth for communication and to the Sun for energy. We'll look at the Earth locking. Because the Earth is rotating and the satellite stays pointing at the Earth, it needs a spin about an axis which is vertical in our picture. So we start with a horizontal vector and we finish with a vertical vector. We can go from one to the other by adding on a vector representing the difference between the two. So we'll start with the satellite spinning about the horizontal axis. When we add on the new spin, the resulting spin is given by the sum of the vectors. The axis of rotation will be vertical, and the satellite will be locked onto the Earth.
Vector algebra is a fundamental tool in the mathematics that we use to analyze spacecraft behavior. In fact, we use several different types of vectors. The angular velocity vector is just one among many. Some others are the angular momentum vector, the satellite state vector, which is effectively a combination of its position vector and its velocity vector.
Our final example of vector spaces comes from a quite different subject: music. Now, you may think music has very little to do with the arrows we used for vectors in our other examples. But in fact, the underlying mathematical properties of musical notes are very similar to the properties we saw before. You combine sounds by adding them, just like we did with the other types of vectors. To see just how this works, we went to the radiophonic workshop in the BBC's Maida Vale studios in London.
Now, John, you've got a lot of equipment in here. What exactly does it do, and what do you do with it?
This studio is used for recording sounds, for analysing sounds, and for manipulating sounds. What I have here is a digital workstation, and using this I can record sounds into it, and then I can look at sounds, strange as that may seem. We can actually see a visual representation of a waveform.
Music, and indeed sounds in general, seem impossibly complicated to analyse, so how can you do that?
Music is incredibly complicated, but what we can do is break it down into its components. So if we were to look at, say, a single instrument playing a single note, we have something to work with. If I take quite a pure sound, say the sound of my tuning fork here, it's just one tone. The simplest sound we can have is a single sine wave, and this I've got on the screen.
So what makes musical notes different?
There are three things. There's the pitch of the note, how high or low it is. There's the loudness or the intensity of the note. And there's also the timbre or quality. that thing that makes a note played by a trumpet sound different to the same note played by a flute. So if we look at those in turn, if we look at the pitch first, here, as I said, we have a sine wave. It's actually at 440 hertz, which is concert A, and it sounds like this. I have underneath it a sine wave at a different pitch. As you can hear, it sounds higher. And if we look on the screen, we can see that there are more waveforms per second in the lower trace. So this is actually at a higher frequency, a shorter wavelength. The second thing that can change is the loudness, or the intensity of the note. Here again I have our sine wave at 440 hertz, but below it I have a sine wave at the same pitch. You can see there are the same number of wavelengths per second, but it's at a lower intensity.
So what's the reason for the difference in the quality of notes?
Well, what we've been looking at so far have been pure sine waves. Now, a real instrument, when it makes a note, has a fundamental frequency, and that's a basic pitch to the note, which is roughly what we've seen so far. But it also has harmonics, or overtones, and these give the note its quality. These harmonics can be represented by sine waves at mathematically related frequencies to the fundamental.
Let's see how these mathematical relationships come about. If you take a stringed instrument, like a cello, then each string will vibrate at a certain frequency, like this. That gives its fundamental frequency. But that same string can also vibrate like this, in two halves. With half the length, you get double the frequency. That's the second harmonic, and it's an octave higher. Vibrating in three parts gives a third harmonic. And you can also get higher harmonics. So the sound produced by a cello is a combination of these different harmonics. The exact combination depends on how the cellist bows the string.
So how do these harmonics affect the sound of a note?
Well, we can start to build up a real-world sound from these sine waves. If we go back to our 440 hertz sine wave here, I have under it two sine waves at related frequencies. The middle one is at 880 hertz, that's twice the frequency, and the bottom one is at 1320 hertz, 3 times the frequency. What I'll do is I'll play the sine wave at 440 hertz and add in the other two sine waves. And what you'll hear is that the pitch of the note won't change, but the quality of the note changes as I add in the other sine waves. And as you can hear, the sound doesn't sound as pure as it did before. We can also look at the combined sound, which is here. And as you can see, it's still periodic, it still repeats itself, but the actual structure of the waveform is now slightly more complicated.
Well, that's fine for combining 2 or 3 sine waves, but if you were given a single sound, how could you tell what sine waves were in it?
Well, if we were to look at the sound that we've just generated, the sound we've just created, it's a single sound, but I can show you a plot of frequency, and that's what we've got down here. Vertically we have intensity again, but this time horizontally we have frequency. And as you can see, there are 3 very distinct peaks at 440 hertz, at 880, and at 1320.
It's a frequency plot like this, which shows how a sound can be thought of as an element of a vector space. In 3-dimensional space, you need to know the size of 3 vectors like these to describe where you are. But we can represent the sizes in other ways. For instance, we could put copies of the 3 arrows side by side. Then the size of the 3 copies also describes where you are. But now, we're no longer restricted to 3 arrows. We could have 4 arrows, and their sizes would represent a point in a 4-dimensional vector space. The more arrows, the higher the dimension. And for sounds, we can let each arrow represent the amount of each harmonic in the sound. The overall sound comes from the combination of all these arrows.
So for a note of a particular pitch, listing the amount of each harmonic could specify a particular instrument, whereas a different list might give you a different instrument.
Oh, indeed it would. I have a recording of a very simple sound, a nice simple instrument, a penny whistle. And I also have a recording of exactly the same note, but this time played by a violin. Now, the first thing you can hear is that the penny whistle is a far simpler sound, and you can see this as well. The waveform for the penny whistle here is much smoother than the waveform for the violin below. We can also look at frequency plots for these two instruments. The frequency plot for the penny whistle looks like this. You can see that there is a fundamental frequency and just a few harmonics, whereas the same plot for the violin gives exactly the same fundamental frequency, but many more harmonics. Now, you can see and hear this more clearly. If I were to start by playing the penny whistle, I'll then play the violin and then go back to the penny whistle again.
Now, if you wanted to build up a really complicated sound, what's the maximum number of harmonics you might use?
It depends very much on what instrument you're talking about and the pitch at which that instrument is playing, and of course on how good your hearing is as well. But for a single note, say, played on, say, a trumpet, you could easily use up to 50 harmonics.
So that's yet another example of a vector space. But it's more complicated than the one we had before. We started with a map. That gave us a 2-dimensional vector space, which we can picture easily. The 3-dimensional space used for buildings is also easy to visualize. Angular velocity gave us another 3-dimensional vector space. And once we understood how it was represented by vectors, we could again picture it geometrically. But for musical notes, we have a vector space which could be 50-dimensional. And though we can look at the frequency display, it's much harder to visualize what's happening. And that's the situation where the power of mathematics takes over.